membrane. And cholesterol also is a precursor of steroid hormones. It is the precursor of what else? Help me, I forgot.
Corticosteroid.
We said steroid hormone. What else?
Corticosteroid.
Chylomicron?
Corticosteroid.
No, these are steroids. Okay, fine. What other the products from cholesterol other than steroid hormones? Vitamin D. Yes, vitamin D is derived from cholesterol. What else? Bile acids are derived from cholesterol. So, what is the objective of this lecture? We talk about the important role of cholesterol, and we already did. The structure of cholesterol, the biosynthesis of, please guys, please. The biosynthesis of cholesterol, regulation of cholesterol biosynthesis, how bile acids are derived from cholesterol and what is the function of bile acid, and how steroid hormones are synthesized from cholesterol and their biosynthesis. So the function of cholesterol, as I said, it is the cell membrane lipid component. It is the precursor of bile acids, and we know that bile acids play a role in the emulsification of lipid, which helps in the digestion of lipid. Okay? And it is the precursor of all steroid hormones, including corticosteroids, mineralosteroids, androgen, estrogen, and all these steroid hormones are derived from cholesterol. And also it is the precursor of vitamin D. Vitamin D3 is the active form of vitamin D, and we studied previously the metabolism of vitamins, right? So that vitamin D is obtained from cholesterol, and it plays a role, as you all know, in the metabolism, in the regulation of the level of calcium in the blood, in the body. So let's talk about the properties of cholesterol. It is water insoluble, it is a lipid. So because it is not soluble in water, how it's transported in the body? It is transported in the body bound to a protein called lipoprotein. And next week, I will explain the lipoprotein metabolism in details. So it has a bad reputation, but it is, as I said, it is essential to all animal life because it is a component of cell membrane, and because of its presence in the cell membrane, it regulates the fluidity of the cell membrane, and it's the precursor of steroid hormones, bile acids, and vitamin D. So why we are afraid from high level of cholesterol? Because when cholesterol accumulates, especially we're talking about the LDL cholesterol, because the LDL, as we are going to study next week, carries cholesterol from liver to peripheral tissues. So the cholesterol will accumulate in peripheral tissues, and this will form on the arteries what we call a plaque. This plaque is composed of oxidized LDL cholesterol. And this will result in increased blood pressure because there is narrowing in the arteries, and also there is reduced ability of the artery to stretch. And because of this, because the artery is narrowed, so we may have a blood clot, and this will lead to myocardial infarction or to what we call stroke. So the presence of cholesterol on the arteries may cause complication due to the hardening of the artery and the occlusion that may occur. So as a structure of cholesterol, it is composed of 27 carbon. We have 4 rings that are fused. We have a peripheral sided chain which is attached to carbon number 17, and we have a double bond between carbon number 5 and carbon number 6. It has low solubility in water because it is a lipid, and we have 2 types of cholesterol. We have the free cholesterol, and this type of cholesterol form only 30% of the total cholesterol, whereas the remaining is present as esterified cholesterol, which is the cholesterol plus a fatty acid that is attached to the OH group, which is the only polar group of cholesterol. So oleic acid, linoleic acid, will bind to the OH group of cholesterol, forming the cholesterol ester. And because the solubility is coming only from this OH, and if this OH will bind to a fatty acid, so we expect that the cholesterol ester will be less soluble or more soluble than cholesterol? less, for sure, because we have fatty acid, so it will decrease the solubility of the cholesterol. So this is the structure of cholesterol. We have, as I said, 4 rings, A, B, C, D, that are fused. And we have a hydrocarbon chain attached to carbon number 17. And the total number of carbon in cholesterol is 27. We have a hydroxyl group attached to carbon number 3. And we have a double bond between carbon number 5 and carbon number 6. The cholesterol ester, as I said, it's an esterification between a fatty acid and the OH of carbon number 3. This is carbon number 3. So we obtain cholesterol ester. Okay, this is free cholesterol, and this is cholesterol ester. And this is the hydrocarbon tail attached to carbon number 17. So 27 carbon for cholesterol. So how we obtain cholesterol in the body? We can obtain cholesterol in the body from the synthesis, or from the stored cholesterol, or from the chylomicron remnant, which is the chylomicron that transport the dietary lipids, so it transports cholesterol from our diet, or from LDL, either from the LDL receptor mediated route, and we'll talk about this next week, or from directly from the LDL receptor. So this slide summarizes the sources of cholesterol. So from dietary cholesterol transported by chylomicron remnant, from the synthesis of cholesterol, and we call it de novo synthesis that occur in the liver, or from the HDL, which is the type of lipoprotein that transport extrahepatic cholesterol from extrahepatic tissue to the liver. So this, in the liver we have a pool of cholesterol, and this pool of cholesterol will serve for the cholesterol that is transported later on to bile acid, or for the free cholesterol that is secreted in the bile. So in the bile we do have free cholesterol, or from the cholesterol which is transported later on by the VLDL lipoprotein, which is the lipoprotein that is responsible for endogenous lipoprotein metabolism, and also we'll talk about this next week. So for the synthesis, we said that we obtain cholesterol from the synthesis, from de novo synthesis that occurs in the liver. What do we need for this cholesterol? We need acetyl coenzyme A. So the acetyl coenzyme A is the starting point in the synthesis of cholesterol. And the start of synthesis, as I said, is the liver cell cytoplasm. So the element that is necessary for cholesterol includes 1, acetyl coenzyme A, which is the source of carbon atoms. And we need 3 acetyl coenzyme A to start the synthesis of cholesterol. And this acetyl CoA can be obtained from the oxidation of fatty acid, as you studied with Dr. Ahmad, or from the dehydrogenation of pyruvate, which is obtained from glucose metabolism, or from the oxidation of ketogenic amino acid. Cholesterol, and this acetyl CoA can be obtained from the oxidation of fatty acid, from pyruvate, or from the metabolism, as you are going to study later on, the metabolism of, you did not study amino acid metabolism yet, right? So you study it later on, oxidation of ketogenic amino acid. Okay, what else we need? We said we need acetyl coenzyme A. In addition to acetyl coenzyme A, we need a reducing power. And you studied in pentose phosphate pathway that reducing power is obtained from an ADPH. So an ADPH is required for the synthesis of cholesterol, which is obtained from pentose phosphate pathway. Also, we need ATP. We need 3 ATP for the synthesis of cholesterol, as we are going to see later on. Okay, so acetyl-CoA and ADPH and ATP. We have 3 major stages or steps in the synthesis of cholesterol. Again, cholesterol synthesis occurs in the liver, in the cytoplasm of liver cell, and we have 3 main stages, and in each stage we have many reactions. So not one reaction here, many reactions in each stage. You can see the arrow, the blue arrow, indicating that we have many reactions. The 3 major stages are: 1, the formation of mevalonate from acetyl coenzyme A, which is called condensation reaction. 2, stage 2, is the formation of squalene from mevalonic acid, which is called polymerization. And 3, which is cyclization and transformation reaction, it's the formation of cholesterol from squalene through the formation of lamosterol. So squalene is will have many perform many cyclization reaction to form lamosterol. We have many reactions here and complicated reaction, and scientists spend years studying this reaction, and then lamosterol is converted to cholesterol. So this is a very complicated biosynthetic pathway for the synthesis of cholesterol, but we have to focus on the major steps, and especially the reactions also of the stage 1, because they are very similar to the formation of ketone bodies. You studied ketone bodies with Dr. Ahmed last week, right?
Yes.
Was it last week? Okay, and he said that ketone bodies including acetoacetate, acetone beta-hydroxybutyrate are synthesized from acetyl-CoA. And the synthesis occurs in the liver, and they are degraded in extrahepatic tissue to provide energy in case you have low level of sugar in the blood. Right? You remember this? I'm sure that he said this, because I saw this in the lecture. Okay? So the step 1, we will focus on step 1, which is the same steps in the formation of ketone bodies. Which means that we have 3 acetyl-CoA that will combine, so it's a condensation reaction to form 3-hydroxy-3-methyl-glutaryl coenzyme A, HMG-CoA. And then the HMG-CoA in the presence of a reductase enzyme will catalyze the formation of mevalonate. So these reactions occur in the cytoplasm of the liver cell. Let's see the reaction. So we start with 2 first, 2-acetyl-CoA in the presence of thiolase. We obtain acetoacetate-CoA, and then in the presence of HMG-CoA synthase, we obtain HMG coenzyme A. And these are the same reaction as in ketone body synthesis, but in ketone body synthesis, the HMG-CoA is then degraded or cleaved by a lyase enzyme.
Oh, so we didn't take that ketone body.
Why?
Why?
Because it's part.
We only took the complex lipids and the.
It's part of lipid metabolism.
Okay, because I thought يعني حضرتك بتعاملين على سناب اللي بيحصل هنا والسناب.
Doctor, we only took how acetyl-CoA, when it accumulates, it forms ketone bodies.
Okay. You mean he did not explain the reaction?
No.
Okay, fine, but he explained that ketone bodies are synthesized from acetyl-CoA, right? So forget about the reaction, because we're studying the reaction here again, but I'm just telling you that the reaction, maybe because he didn't want to have repetition. He's sure that I will explain, but I'm sure that he explained ketone body synthesis. If he did not go through the reaction, so no worries, because these are the reactions. Okay, same reaction, but in HMG, for the ketone bodies, the HMG-CoA is cleaved by a lyase enzyme to form the ketone bodies. Okay? But I'm trying to say that cholesterol biosynthesis and ketone body synthesis share same reaction, and these are the reactions. So if you open the book, you will see that these are the reaction for ketone bodies and for cholesterol. Alright? So don't worry. We'll ask you about this reaction. So then, in cholesterol, so in ketone bodies, this will be cleaved to 4 ketone bodies. In cholesterol synthesis, this one will be reduced by HMG-CoA reductase to form mevalonic acid. So this step is only for cholesterol synthesis, where HMG-CoA is reduced to mevalonic acid. And we need here, as you can see in this reaction, Na2 and ADPH that are oxidized to form NAD2 and ADP+. Okay? Now please focus on this enzyme, because this is the rate limiting step for the synthesis of cholesterol. You are a physician, you will treat the patient having hypercholesterolemia by inhibiting this enzyme. So the drug that you are going to prescribe to your patient will target this enzyme. It will inhibit this enzyme because this is the rate limiting enzyme in the sense of cholesterol, so you can inhibit it by competitive inhibition. We'll talk about the drugs later on. So the stage 2, I will skip these slides because I can explain better here. So in stage 2, mevalonic acid is phosphorylated by 1, 2, 3 ATP and decarboxylated to form isopentenyl pyrophosphate. Then the isopentyl pyrophosphate is converted to dimethyl allyl pyrophosphate, and then the dimethyl allyl pyrophosphate with another IPP, which is isopentyl pyrophosphate, and a transferase enzyme will form geranyl pyrophosphate, and geranyl pyrophosphate with another IPP will form farnesyl pyrophosphate, and then farnesyl pyrophosphate will be will form squalene in the presence of squalene synthase. So step 2 or stage 2 is from mevalonic acid to squalene. Are we going to study these reactions? No. Don't worry. We'll never ask you to memorize this reaction because this reaction will help in nothing. So there is no disease related to this reaction, there is no drug related to this reaction, so no need to memorize this reaction. But what you should know that isopentyl pyrophosphate, geranyl pyrophosphate, and farnesyl pyrophosphate are metabolites in the synthesis of squalene. Okay, so you need to know these 3 steps, major steps, and you need to know the name of the metabolite, just the name of the metabolites, and the requirement. I mean ATP and NADPH. So precursor, the first step in details, for the second step and the last step, you just need to know the name of the metabolite. So for step 2, mevalonic to squalene, we have isopentyl, geranyl, farnesyl pyrophosphate to form squalene. And for step 3, which is the cyclization reaction of squalene, so squalene, again we need an ADPH here. In the presence of squalene monooxygenase will form lanosterol, and it's not one step only, it's many reactions here. And then lanosterol is converted to cholesterol, which is the final product in this biosynthetic pathway. Do I need to know what you have to study in this pathway, or it's clear? You didn't get it? Oh my God.
Looks simple. It looks easy.
It is very simple. So we go again to the stages. So the stages for the synthesis of cholesterol are stage 1 from acetyl-CoA to mevalonic acid, stage 2 from mevalonic acid to squalene, and stage 3 from squalene to cholesterol via lanosterol. And this is the cyclization reactions. Okay? Now we have many reactions here and many reactions here, but these reactions you have to study because you have a drug that works here. So you have to know in detail stage 1. Whereas for stage 2 and stage 3, so you just need to know the name of the metabolites. So stage 2 is from mevalonic to squalene. We said that we have many reactions. Here actually we're showing some of these reactions. Because you can see here we have reaction that we did not mention here. We have also here reaction that we did not mention. Look here. We have many reactions, so no need to study the details of the reaction. So just to know that mevalonic is phosphorylated and decarboxylated to form isopentyl pyrophosphate, and then geranyl, farnesyl, and squalene. That's just the name of the metabolite. And if I ask you, geranyl pyrophosphate is one of the metabolites for the synthesis of fatty acid, triacylglycerol, phospholipids, and cholesterol. So you should know that the synthesis of cholesterol. Or I may ask steroid hormone synthesis. So it's cholesterol, just the name of the metabolites. Okay, clear? Now, what we need to know is the regulation. I said that the synthesis of HMG-CoA reductase, the synthesis of HMG-CoA is the synthesis of mevalonic acid from HMG-CoA in the presence of HMG-CoA reductase is the regulatory reaction. So we can regulate the synthesis of cholesterol through this reaction via 3 regulatory mechanisms. One is covalent modification. And you know very well what we mean by covalent modification. This enzyme, HMG-CoA reductase, when it is phosphorylated, it is inactive. How it is phosphorylated? By a cyclic AMP-dependent protein kinase. So the cyclic AMP-dependent protein kinase will phosphorylate HMG-CoA reductase, so it will inactivate HMG-CoA. Do you know how this pathway is stimulated via which hormone? Glucagon. So in other terms, glucagon inhibit or stimulate HMG-CoA synthesis or cholesterol inhibit. So glucagon inhibit cholesterol synthesis and insulin stimulate cholesterol synthesis. Okay? Another pathway, another regulatory mechanism is through the half-life of the enzyme, which depend on the level of cholesterol. And the most important one also is the gene expression. So the cholesterol level can be controlled by the amount of messenger RNA, which means, so this is the reaction again. HMG-CoA reductase. It is the enzyme that form mevalonic acid. So it is inactive when it is phosphorylated, as I said, and the dependent protein kinase enzyme will phosphorylate it, and when it is dephosphorylated by a phosphatase enzyme. So the phosphatase will activate HMG-CoA, and when it's active, it will form mevalonic acid, and then mevalonic acid will form cholesterol. Now, this cholesterol, when it accumulates, it will inhibit the synthesis of HMG-CoA reductase. So when excess amount of cholesterol will inhibit the synthesis of the enzyme via gene expression. So what is the regulatory element here? It's called a steroid regulatory element binding protein, which is bound here in the endoplasmic reticulum to a cleavage activated protein, steroid cleavage activated protein. And it is when there is low level of cholesterol, this will move to Golgi apparatus, and it's cleaved by proteolytic enzymes, and then the steroid regulatory element binding protein will activate the regulatory element, which is the steroid regulatory element on messenger on DNA, which will stimulate the messenger RNA, and the messenger RNA is translated to form the enzyme. So excess of this enzyme will inhibit the formation via gene expression, and the low level of cholesterol will stimulate this pathway to stimulate the expression of messenger, the formation of messenger RNA, then the formation of the enzyme by translation. Clear? No?
Yes.
It should be clear. So why it is bad? We said that because it is associated with heart disease. So the accumulation of cholesterol will lead to what we call atherosclerosis, which is the formation of plaque on the arteries, which will narrow the artery, and this will cause myocardial infarction or stroke. When the studies showed that high level of cholesterol is related directly to heart disease, and the low level of cholesterol is associated with decreased rate of mortality and morbidity. So that's why you have to make sure you have to control the level of cholesterol in your patients, especially patient having family history of cardiac problem. So let's take a case study. Your patient is 50-year-old male. He has a family history of cardiovascular disease. Although he is under strict dietary control, but his serum cholesterol is 8 millimole per liter. When we consider it in millimole per liter, it should be below 5 millimole per liter. And if we are taking the milligram per deciliter, it's below 200 milligram per deciliter. So that's why he has hypercholesterolemia, and the physician will start putting this patient on pravastatin. And after 3 months, you have to check the level of cholesterol. It decreased to 5.5. So what is pravastatin and how it does work to control the level of cholesterol? What I want you to know that it's very important to follow up with the patient, because some patients will respond to one type of statin, other will respond to another type of statin, because this is what we call personalized medicine. So you don't have the genetic structure of the patient that is 100% similar. So because of this difference in genetic, the gene that form the protein that enter in the metabolism of the statin, which is the drug, may be not the same in all patients. So some patients will have will respond to the treatment, other they may need another type of statin. So it's very important to follow up with the patient and make sure that we had a study last year with Dr. Bara on statin, and we showed that patients having myopathy, because it is well known that patients taking statin may have muscle pain, and they may stop taking statin without consulting the physician. This is very bad. So the myopathy, we showed that the myopathy is associated with the gene polymorphism, which is the gene that make the enzyme that is involved in the statin metabolism. So if this gene polymorphism exists, so the drug is not metabolized, so the patient will have high level of this drug in blood, so he may have more symptoms of myopathy. So it's very important to before now for such treatment we don't apply unfortunately personalized medicine. We do it only for research purpose, but later in the future years I'm sure that before you will give any drug you have to make sure what is the genetic structure of your patient. You know, we're doing this for chemotherapy now. You know. So the drug will inhibit the rate-limiting enzymes, which is HMG-CoA reductase, and this drug is one of the statin family. It's derived from penicillin strinol, and it has the inhibiting property because it is a competitive inhibitor of HMG-CoA reductase, and it caused a decrease in the LDL cholesterol 20 to 40% and increase in LDL receptors. You know that we need the receptors for the metabolism of cholesterol, and we will study this next week. So this is the drug, the simvastatin. It has a similar structure to the substrate, which is SMG. Okay, because of this similarity, as you know, what happened? So they will compete for the active site of the enzyme, and the drug will bind to the active site instead of the substrate. And this will cause inhibition of the formation of cholesterol, of mevalonic acid, thus cholesterol. So how cholesterol is degraded? We know very well that cholesterol cannot be broken down by mammalian cells, so it is removed. We have removal mechanism of cholesterol. One is in the gut, we have cholesterol that is transformed into the feces, or it is converted to bile salts. 50% of the total cholesterol is converted into bile salts, or in the gut also we have bacterial reduction that transform cholesterol into neutral steroids. So what are bile acids and how they are synthesized from cholesterol? Bile acids are amphipathic because they contain hydroxyl group. We have from 2 to 3 OH group attached to the rings, the 4 rings. It contains 24 carbons, so by we can tell that there is shortening of the, because in cholesterol it's 27, here 24, so there is shortening in the length of the hydrocarbon chain, and also there is hydroxylation reaction because we have more OH, okay, and depending on the type of the bile acids compared to cholesterol. In cholesterol we have 1 OH, so the synthesis of bile acid from cholesterol occurs by hydroxylation reactions. So here we have 2 types of bile acids, cholic acid and chenodeoxycholic acid, that are derived from cholesterol. What is the difference between bile acid and bile salts? A bile salt is a conjugated bile acids, and it is conjugated to either glycine, so this is for example cholic acid with glycine, it forms glycocholic acid, which is the bile salts. And here a conjugation of chenodeoxy acid with taurine, and it's called tauroechenodeoxycholic acid, which is another example of bile salts. So what I want you to know that the bile salts are the conjugated bile acids, and the conjugation occurs to either glycine or taurine. Okay? So the cholesterol, as I said, is the precursor. By hydroxylation reaction, we obtain cholic acid, and this reaction is inhibited by the product, which is cholic acid, and it's stimulated by the substrate, which is cholesterol. Now, you know very well that the bile is a mixture of phospholipids and bile salts, and it is synthesized in the liver and stored in the gallbladder. So let's talk more about the synthesis of bile acids. Primary, we have 2 types of bile acid. We have primary and secondary. The primary bile acids are synthesized from cholesterol, and they are conjugated in the liver to bile salts. So synthesis occurs in the liver, and then they are excreted in the bile duct to the duodenum, and in the duodenum the primary bile salts are hydrolyzed to give back primary bile acids, and in the duodenum the primary bile acids are converted to secondary bile acid. Then the secondary bile acids are excreted in the blood and taken by the portal vein to the back to the liver, where you have conjugation of the secondary bile acid to form secondary bile salts. So what I'm trying to say here, that primary bile acids are synthesized in the liver, but secondary bile acids are derived from primary bile acids in the duodenum, but the conjugation of both occurs in the liver. Okay, and they are stored in the bile, in the gallbladder. What happens if you have deficiency in the bile salts? This will lead to a condition called cholelithiasis, or another term, gallstones. So accumulation of stones in the gallbladder. And this can be, the stones are made of cholesterol, and it may occur because of increased excretion of cholesterol, and also it will happen with the use of fibrates. These drugs can cause the accumulation of gallstones in the gallbladder. And these stones, because they are small, they may cause obstruction of the bile duct. The only way to treat the cholelithiasis is cholecystectomy, so we need to remove the gallbladder. Okay, this is the only way, and we have to make sure if you have small stones, it's more dangerous, more complicated than the large stones, because they may pass in the bile duct and cause the obstruction. So the only way is to remove the gallbladder by surgery. Now, one more importance of cholesterol, it is the precursor of steroids hormone, and these steroids hormone include the glucocorticoids, and I mean here the cortisol, the mineralocorticoid, and I mean here the aldosterone, the androgen, which is the male sex hormone testosterone, the estrogen and the progesterone, which are the female sex hormones. So all these hormones, steroid hormones, are synthesized from cholesterol. It is the main precursor, and we have a series of enzymatic steps in the mitochondria and the endoplasmic reticulum of steroidogenic tissues. I mean tissues that form the steroid hormone, where they convert cholesterol to steroid hormone. The rate limiting step of this is the transport of cholesterol from the cytoplasm into the mitochondria, and this occurs by a regulatory protein called steroidogenic acute regulatory protein. So once the cholesterol is transported to the mitochondria, the synthesis of steroid hormone occurs. So this cholesterol is the precursor of all these steroid hormones. We are not going to study the details of the synthesis of steroid hormone, okay? Because this is part of the physiology. You will take it in hormones. But I want you to know that cholesterol is the precursor. It gives the testosterone, the androgen, the cortisol, which is the glucocorticoid. Why it's called glucocorticoid? Because it regulates the level of sugar rate. High level of cortisol may cause hyperglycemia. And the androgen, which is the mineralocorticoid, which is aldosterone, which regulates the level of sodium and potassium. That's why it's called mineralocorticoid. Have you studied this before?
Yes.
Okay, very good. Now, what I want you to know from this slide, that any deficiency in one of these enzymes will lead to a group of disorders called congenital adrenal hyperplasia. And I don't want you to study all these because they are very rare. The only common one is this one, which deficiency in the enzyme 21 hydroxylase enzyme. It forms 90% of the congenital adrenal hyperplasia. And this will lead, when you stop the synthesis of, so the enzyme will stop the synthesis of deoxycortisol, so you will have decrease in the production of cortisol and aldosterone. So this will lead to a problem because these two hormones are important in the regulation of the minerals, and you have overproduction of sex hormones, steroid hormones. So this will lead to the overproduction of androgen, will lead to masculinization of the external genitalia in females, and early virilization in males. So sexual complication may occur because of the overproduction of these hormones. So this is the only one that I want you to study from this slide, this disease. Okay? And for the other slides, no need to study because, as I said, you will study it in physiology. So the cortisol, how it is secreted and how it's regulated, this is pure physiology. Aldosterone, which is the mineralocorticoid, it regulates sodium, potassium. Androgen, which is secreted from the inner and middle layer of the adrenal cortex. And this slide shows the adrenal cortex which is responsible for aldosterone and cortisol, the ovary for estrogen. So all these slides starting from here, no need to study, it's extra information for you, but I will not ask you about it in the exam. Okay, I will not ask questions on these because this is physiology, done by chemistry. Do you have questions concerning the first part? No? It is easy. So as I said, please make sure to study cholesterol biosynthesis, the first step or stage, which is the formation of mevalonic acid in details. As for the other, no need, just to know the name of the metabolites and the major steps only. So mevalonic to squalene, then squalene to cholesterol, and to know just the name of metabolites. Okay, so you know that these metabolites are involved in the biosynthesis of cholesterol. And what is important is to know the regulation of cholesterol. For sure, I will ask you about the regulation of cholesterol. Okay, this is what is important, and to know the function of cholesterol. All right. Thank you. See you next week.